we're going to talk about some special segments that exist in our triangles. So we start with one called the altitude. The altitude of a triangle starts from the vertex and extends perpendicular to the opposite side. So I'm going to pick this point right here, and if I drop a perpendicular line to the opposite side, it's the altitude. Now, did it necessarily bisect over here? Did it cut this side in half? Not necessarily. Now, there are 3 altitudes in this triangle. I could draw them all if I wanted to. I could draw an altitude from this perpendicular to the opposite side, and I'm just going to draw one of them for now. And then I'm going to get to the median of my triangle. The median starts at the vertex again, but this time it goes to the midpoint of the opposite side. So my median, I'm going to make up a midpoint here just with my eyeballs. So the median would go like this, to the midpoint of the opposite side. Now, to illustrate the rule we're going to learn about medians, I need to draw all 3 of them. So I'm going to pick a midpoint of this side, and I'm going to draw another median. And then, let's say that's the midpoint, and I'll draw the 3rd median in this triangle. Notice that all of our medians intersected at the same point. That point is called the centroid. It's kind of a cool word. The centroid is the center of gravity of the shape. So for example, if I made this triangle out of solid wood and I found this centroid, I could balance it on the tip of my pen. Well, maybe not my pen, but balance it on the tip of something, because that would be the center of gravity. Just an interesting fact. This is called the point of concurrency. It's free of charge. You're not going to be tested on this part. A point of concurrency, when all 3 of them meet at the same place. The point of concurrency, if I intersected all of the altitudes, would be called the orthocenter. Again, you don't need to know that. It's free of charge. But the centroid is very important, because what the centroid does is it is 2/3 of the distance from the vertex to the midpoint of the opposite side. So let's say I'm going to label this ABC. So this point B is 2/3 of the distance from A to C. So I'm going to label from A to B as 2/3 of the distance, then B to C is the other 1/3. Now here's the easiest way I like to think of it. Think of the segment AC and split it into 3 pieces. So if I put a dot here, so from A to C I'd have 1, 2, 3 sections. AB got 2 of those sections, BC got 3 of those sections. So for example, if I told you that AC was 21, and we wanted to figure out AB and BC. Those of you who don't mind the fractions can just say, hey, 2/3 of 21, and I've got AB. But if you want to do this in your head without a calculator, let's divide 21 into 3 pieces. 21 divided by 3 is 7. So the shortest piece is 7. The longest piece is 2 7s, which is 14. So also notice that AB and BC, AB is twice as big as BC. So think of it as 3 pieces. AB gets 2 of those pieces. BC is the other piece. So that's the importance of the centroid that you're going to see later. The angle bisector of a triangle. So the angle bisector is just what it sounds like. It bisects an angle. It doesn't do anything else. All of these special segments have one job. Altitude is perpendicular. Median goes to the midpoint. Angle bisector bisects an angle. So I'm just going to eyeball these and do a horrible job of it. There's an angle bisector. let's say I tried to draw this angle bisector, and then I drew another angle bisector. Looky there. We have a point of concurrency for our angle bisectors. It's actually called the in-center. And I would draw this, but I would do a horrible job. This is the center of a circle that is inscribed in the circle. So if I were to, like I said, I can't do it, but if I were to draw a circle that touches all three sides, that would be the center. Obviously, my circle is not the right circle, but that's the idea. It says here that a point on the angle bisector is equidistant from the two sides of the angle. Okay, if equidistant is a new word, it's just what it sounds like. Equal distance. So if I've got my angle bisector, let's see if I can draw you a little picture of it. Right here, this is going to be the angle bisector. Then what we're saying is if I pick a point and I measure the distance from my point to that side, and then I measure the distance from my point to this side, that these two distances would always be the same if that's an angle bisector. And why did I put the little box there? Because how do we measure the distance from a point to a line? Remember, it always has to be perpendicular from a point to a line. So you may see some questions involving that rule. A perpendicular bisector. Now this one has two jobs because he's got two terms in its name. It's perpendicular to the opposite side, and it bisects the opposite side. So it goes through the midpoint of the opposite side. Now this one doesn't have to come from the vertex. It can, but it doesn't have to. So if I want to be the perpendicular bisector here, let's say that's the midpoint. If I want to be perpendicular, I would have to be like this. Notice that's not going to go to the vertex if I continued on. It's perpendicular and it bisects. So it does those two things. Now, here's the little rule that goes with perpendicular bisectors. It says every point on the perpendicular bisector is, I'm going to use that word equidistant again. Remember, that's just what it sounds like. Equal distance is equidistant from the endpoints. So let's say I picked a point right here and I measured to this endpoint and to this endpoint. According to this rule, those would have to be congruent to each other. Maybe I went from this point to each endpoint. Guess what? Those would have to be equal to each other, and so on. So any point on this perpendicular bisector is the same distance to the endpoints. So those are our special segments. You will want to learn their names and be able to recognize them in pictures. This rule is very important, the rule about the centroid. You'll practice that. And the angle bisector and the perpendicular bisector, you'll practice that a little bit as well.